Welcome back to Tracing the Sky. So in the last episode, we looked at Mercury and Venus and what makes their motion a little peculiar compared to Mars. Now, they all seem to do this wandering with retrograde motion, but what sets Mercury and Venus apart is that they stay really close to the sun. They never get too far away from the sun. And that's really peculiar. Now, they switch sides of which side of the sun they are on, but they seem to get further away until a certain point, and then, like they're on a leash, come back around to the other side of the sun before resuming that cycle. So today I want to show you how Ptolemy modeled this. A lot of similarities to the model of Mars, but there's one particular difference that I want you to see. And this will have really important implications as we move forward with our story and look at how the history of astronomy progressed and how we ultimately get a shift in our thinking. So let's dive into Ptolemy's model of Mercury and Venus. Okay, so here we are looking at the model of Mercury, and you'll see a lot of elements that are very similar to what we saw with Mars. You've got Earth off-centered from the center of this deferent, right? You've got an equipoint here. You've got the center of the epicycle going around the deferent. You've got Mercury here going around an epicycle. And the one main difference here is we're also going to see the sun. And Ptolemy essentially takes this epicycle motion and ties it very closely related to the sun. The kind of deferent is anchored to the sun. So let me just play this motion so you can get an idea of how it works. So I'm going to play this, and you're going to see that the planet here, Mercury, is going around its epicycle, but that the deferent and the sun are kind of aligned with each other. And I think what you'll start to see is how this mimics what we saw in the sky when we tracked Mercury over the course of time, right? You can imagine there's a star sphere around here too, and they're both moving through the stars. You can see that Mercury is going to appear on either side of the sun, right? So from the perspective on Earth, Mercury is on one side of the sun, then its course around the epicycle causes it to go around the other side. It's still going around the equipoint, so that changing of speed is still going to happen. But it's now never getting too far away from the sun. And I want to show you another way of looking at that so that you can really see how it stays that fixed distance or fixed maximum distance away from the sun. So let's look at that next. So what I've done here is added some line of sight. So we can imagine us looking at the sun and then us looking at Mercury. And we can measure the amount of turning, right? We just measure that in angles. So we can measure this angle here as the amount of turning if you were looking at the sun and then you turned your head to look at Mercury and how much turning you've done. And what you'll be able to see is that as Mercury goes around the epicycle, the amount of turning changes. It can get larger, right? So now we've increased the amount of turning. And then as it goes around the epicycle here, it starts to get smaller, right? We've cut the angle about in half. And then eventually it's going to be directly in line with the sun. And then that angle is going to get larger. And there will be 2 points where the angle is the largest. And you remember I mentioned this last time. If you were to measure the angular distance of Mercury, it's never going to get more than 28 degrees away from the sun. And so this model fits that, right? As Mercury goes around the epicycle, there will be a couple points on either side of the sun, 1 point on either side of the sun, so 2 points total, where the angular distance away from the sun is its maximum. And we saw that. We saw that Mercury would go kind of cross over the sun until a certain point, get as far away as it can, get on that leash and come all the way back around until a certain point. And so this mimics that perfectly and helps explain that really well. And so this is how Ptolemy models Mercury and Venus. Shares a lot of the same elements as Mars, right? It's got the equipoint, the epicycles, the deferent. But it has this unique idea where it's following the sun, right? The deferent never gets too far away from the sun, and the epicycle never gets too far away from the sun. And that's what sets it apart. So next, let's wrap up Ptolemy and kind of do a little reflection on him and where we sit in the history of astronomy. Because as I've said before, he's a really important figure. And so we want to wrap him up and set the stage for what's going to come next. So we've come a long way with Ptolemy, right? Ptolemy has shown us how to look at the world geometrically and mathematically. we're able to think about things with a level of mathematical precision that we just haven't had yet. For much of what we've been doing in this series, we've been looking at our observations and we've imagined what might be happening, and we've thought a little bit geometrically. But with Ptolemy, we're really seeing what mathematical precision looks like and means. And it's not really that complicated, right? In the sense of what he's doing, we're just looking at circles with a set radius and then calculating intersection points. Now some of the math can get kind of complicated, but conceptually, that's all we're really doing is we're thinking about how to express the reality of what's out there in these shapes that have mathematical properties and trying to understand how to move all of these shapes at certain ways with these properties in order to predict where planets and stars and the sun are going to be in the future. And Ptolemy's model is very, very good at that. I've kind of mentioned this before. It's going to be over 1,000 years before somebody comes around and disproves it. So Ptolemy's model is able to do something to a level of accuracy that no one had done before. And there's a lot of practical values to that for them back in the ancient world, right? They don't have calendars on their smartphones they can look at. So being able to accurately predict things is really important. Now, we've got some open-ended questions, and people back then would ask some questions about Ptolemy's model, right? Because there's kind of this interesting question of, is this really what's going on, right? Is there really an equipoint or an epicycle or a deferent? Are there actually things there? It's a little like my take on it, or what I've come to understand, is that they didn't take this super literally at this point. They weren't really as concerned with physical causes, like why is there this epicycle? They were much more forgiving because a lot of the primary concern was practical results. Could your model work? And Ptolemy's model certainly did that. Now, there is a question, is there anything here? And that's probably the biggest weakness of the model is, well, why is there this equipoint, right? Why is there a point off-centered from where the Earth is that this epicycle is going around? And why is the planet going around this point with nothing there? There's nothing we see where the center of the epicycle is. So why is the planet going around this arbitrary point? That's really like where some of the puzzling things happen. Yes, the math works, but there's no explanation of why it works, why things are happening. And so that's an important open question and shift that's going to happen. Now, one other interesting kind of objection some people had, or concern people had with Ptolemy's model is, they were a little bit unsure whether he was sticking to that really core tenet of uniform circular motion, right? We've looked at this for a while now, that a really important principle to them was that the heavenly bodies moved in uniform circles, right? Constant speeds. And yet Ptolemy's kind of doing a bait and switch a little bit, right? He couldn't make it work where the center of the epicycle is going at a constant rate around the Earth. And so he had to add this other point that was moving at a constant rate. So this pink line is moving around the equipoint at a constant rate. But because it's not at the center of the deferent, it causes the epicycle to speed up and slow down. And so some people were a little critical of this because, well, now the deferent isn't really moving at a constant speed. It is speeding up and slowing down around its circle. His model was so good, though, that people had to use it. They couldn't ignore it. So despite that kind of inconsistency or deviation away from uniform circular motion, his model was accepted and used. There's one other flaw in his model, but I'm going to save it for our next discussion. We're going to fast forward now because not a whole lot is really going to happen. I mean, there's going to be some minor advances in astronomy, and the Islamic Empire is going to take Ptolemy and think deeply about it. But it's going to be, like I said, over 1,000 years before we're going to get anything substantial. And so in the next episode series, we're going to be focusing on Copernicus, a name you've probably all heard. And we're going to be looking at his revolution in astronomy and what is so significant about it. But we're also going to get to see the way he tackles it and how he approaches solving that problem. And so in that series, we'll look at one of Ptolemy's flaws in his model, and it's particular to his model of Mercury and Venus, but I'll save it for our discussion on Copernicus because that's really important to how Copernicus is going to try and build some credibility for his model. So I hope you've enjoyed this series on Ptolemy. I've really enjoyed bringing it to you, and I hope you can see why Ptolemy is such an important figure in astronomy. And I hope you've really come to understand what it means to think about the world geometrically and mathematically. So I hope you'll continue the series and join me as we start to explore Copernicus and the revolution that's going to come with his model of the solar system. I'll see you next time.